Hello, I'll present basic learning materials for Malicious App Analysis. First of all, it's a table of contents. First, the Android concept will cover the concept of Android and the execution environment. Next is the Android component. We'll talk about Android's components and activity lifecycle. Third, I'll introduce the Android dynamic debugging tool. Finally, we'll deal with the analysis methods and introduction of malicious apps through the above. This slide is about the concept and the execution environment of Android. Android acts on top of the Linux kernel by default. The main components of Android are shown in the figure. The application layer is an area where applications like SMS programs, calendars, maps, and browsers are loaded. Applications are developed by Java language. The application framework layer is an area that provides APIs for application development. The API allows developers to express buttons or text on the screen and access data of other applications, such as address books. This layer also provides APIs for managing the lifecycle of applications. The library section layer is an area that provides various C/C++ libraries that are available on Android. All libraries in this area are accessible to developers through application frameworks. WebKit supports browser functionality. In addition, SQLite is a database engine for embedded use. Next is Android runtime layer. Android works on Java, but it works on Dalvik Virtual Machine or DVMs, not Java Virtual Machine or JVMs. So the Java source is compiled into a class file by the Java compiler. Finally, the Linux kernel layer. Android is based on the Linux kernel, which provides security, memory management, process management, network stakes, and various drivers. This slide is about the components of Android. The Android platform consists of activity, service, broadcast receiver, and content provider. The activity component is the most commonly used part. Basically, the activity component is developed through defining and implementing the lifecycle method because it requires the inheritance of activity classes from Java sources. The service component refers to a process that runs in the background when using a smartphone. Although it can't be seen in the actual user, this component is needed for the Android actual works. Content providers are the components that manages and provides data for applications. For example, it manages data through file input and output and SQLite DB. The last component is the broadcast receiver. This element is a component that receives various events and information from Android. These components are used as an entry point within the Android application to run tasks independently. These various components that exist within an Android application can be easily invoked by other Android applications to perform the desired task. This characteristic makes the application more flexible and reusable than applications in other mobile platforms. The Android activity lifecycle collectively refers to changes of status, such as activity being created, stopped, played, and terminated, and the callback method. The figure on the right is an illustration of the activity cycle in the official Android document. Major callback methods such as onCreate, onStart, onResume, onPause, onRestart, onStop, and onDestroy are shown. Let me explain 4 major callback methods. OnCreate is a function called when an activity is first created, and onStart is a function called before the activity is restarted. And onResume is the step in which the activity is visible on the screen, and onRestart is a function called when the activity is stopped and recalled again. OnPause is a function called when an activity is unloaded to another activity and the focus is lost. And onStop is a function called when it is 100% on the screen. Finally, onDestroy function called when the activity completely disappears from the stack. I gave you a brief description of the components of Android and how it works. Next, I'll explain what dynamic debugging tools you use to debug before analyzing malicious apps. We actually use JEB frequently in malicious apps analysis. JEB Android Decompiler is a reverse engineering platform that allows packaged APKs to decompile as a Java code to make the code readable and debuggable. As you can see on the screen, when you upload a malicious app to the JEB, the malicious app is decompiled and executed with a test code that is easily readable for the user. The function of JEB is to decompile Java source code into Dalvik bytecode. No DAX2JAR conversion tool is required. This JEB decompiler is even considered a small difference of Dalvik. Thus, JEB decompiler is useful for metadata. Analysts also need flexible tools to deal with obfuscated or protected code. JEB's powerful UI allows users to find cross-references, rename method, fields, classes, explore code, and data, and comment on them. The basic UI is shown in the slide and is providing various functions with easy use. Among them, like IDA's hexray function, it provides a function to decompile to Java for easy analysis of bytecode. For more information, visit the site below. As you can see on the screen, when converting this bytecode to Java source code for easy viewing, you can use Tab and Q keys to decompile. The screen shows the hard-to-see bytecode is being converted to Java source code. Next, the shortcut key / is used to annotate the role of the class in the analysis stage. In practice, the file name and class name of the class can be changed, and the function can also be used to indicate the role of the function. The shortcut key X in the second figure tells you which function you are calling by referring to when you make a call. The shortcut key X is convenient when you want to know referring classes and referred classes. Basically, we use a lot of dynamic debugging tools to analyze malicious apps. However, if it's difficult to use JEB because it's a commercial tool, you can use static debugging tools. Next, I'll briefly talk about static debugging tools. From this screen, the Apk file is in the form of a compressed file, and when extracted, it contains multiple resources, source codes, classes, and DAX files. Using the Apk tool, a Java-based utility, you can decode the app file and extract the SMALI, so and resources files. Static analysis is performed to analyze the protection of the app itself and to check whether sensitive information is stored in the source code or repository without the mobile app running. Tools required to perform static analysis include Apk tool is a necessary tool for binding, decoding Apk files. The DAX2JAR is a tool for extracting jar files. JDGUI is a tool for decompiling Java. The sequence of tasks is started from extracting Apk file to user's computer through pull command in ADB. Then depack the Apk file using the Apk tool. Next, extract the jar file from the Apk package file using DAX2JAR. Finally, obtain the detailed Java source code from the jar file using JDGUI. Then, we can analyze the Java source codes of malicious app. From the next slide, I'll explain these steps with more details. First of all, attach your PC to a rooted smartphone or emulator using ADB. And use pmlist packages -f grep app_name.apk command to search for package files using ADB. After that, bring the app to PC using ADB pull command for static analysis. The command is ADB pull data app apk name. Next, install Android framework for depackaging, then depackage the Apk file. The command word is java -jar apktool.jar if app_name.apk and java -jar apktool.jar d app_name.apk. If command is a command that releases sources such as framework files, dcommand means decode. After this step, you'll be able to explore the depacked files on the folder named as the apk package. Finally, extract jar file from apk file using dex2jar. The command word is dex2jar.bat, location of apk.apk. After you execute the command, you'll be able to see the source code as shown in the picture when you attach the jar file using JDGUI. Before we start analyzing malicious apps, I'll briefly explain the app's installation process and dynamic process. First of all, you need to set up the Android development environment. As shown in the picture, you need to download and install JDK, Eclipse, and Android SDK. Then link JDK and Android SDK in Eclipse. When you develop Android after configuring the environment, the Android Apk file is created by compressing into a zip file as shown on the right. The Apk file, which is built from the developed Android application, you can install it using ADB. The Apk file will be installed at the user level, and Android will operate on top of the Dalvik virtual machine. The packed app encrypts the classes.dex file possessed by Apk and decrypts it dynamically at runtime. Because of this characteristic, you need to execute Apk file through the Android emulator. Then download the memory dump of decrypted codes using an open-source unpacker. Next, I'll explain how to unpack the QIHU 360 company's packaged apps using the Unpacked Unpacker. In this slide, we'll overview the voice phishing using malicious apps. Attackers send smishing text messages, which should look like a loan advertisement. If the victims respond to the smishing text message, then attackers lure victims to access mobile phishing sites. If the victim then downloads and installs a malicious app from the mobile phishing site, key information of the infected device is leaked to the CNC server. If you call the representative phone number of financial company from the infected device, the outgoing phone is intercepted by a malicious app and connected to the attacker's phone number, which then leads to real financial assets damage through social engineering techniques. This slide is an overview of bodycam phishing using malicious app. Bodycam phishing is a scam that using bodycam and hacking apps. The process is something like this. Attackers seduce people to do bodycam and lure users to install a hacking app. Then attackers record the exposure photos or videos and use those to threaten users. Most of patterns started from using random chat apps such as YoungTalk, Z1A Talk, and SimTalk on smartphones. While talking on those apps, the attackers ask victims to change the chatting apps that can or are compatible with PC, such as Skype, Line, and etc. The main repertoire is to show the sexual activity of each other through a video call using a video call service. When you make a video call, you see a woman who is completely exposed. It then encourages you to expose your penis, asking you to show that you are a man. And they ask for a face to appear on the video call. While making a video call like this, he sends an APK with saying, like voice is unclear or that the video quality is bad. The attackers say that it's because their phone is BlackBerry, so you need an integrated sound support app or she will send her photo album. As soon as this app file is installed and executed, the victim's personal information, such as your contact information, GPS, ID, and password of the saved site are leaked. The following is how malicious apps are distributed. The first picture in this slide is a real case experience by a customer of a certain bank. After receiving an SMS containing a link to a malicious app distribution site, the customer reported it directly to the customer center of the bank. If a user clicks the link, it will connect to the certain bank mobile phishing site and downloads malicious apps from the phishing page. If user downloads and installs the malicious app, the app will intercept the phone call to the representative number of financial institution and connect the call to the attacker's set phone number. The victim, who misunderstood the attacker as an employee of a financial company by the intercepted call, will be suffered financial damage while following the attacker's instructions. The second picture shows a smishing text message through Messenger app. This case shows attackers pretend to send a video link to lure users. If users click this link, users will be taken to that phishing site, which will download malicious apps. Downloaded malicious apps steal key information from victim devices or connect to phishing apps, which will cause financial damages. The last picture shows a financial company's mobile phishing site created to distribute the malicious app. If users click the link from attackers, then users will be connected to this phishing site and download of the malicious app will be started. The phishing website is customized for each financial company. In other words, most of the image files used on phishing sites are from the original websites of financial companies. Thus, it is hard to recognize whether it is a phishing site. Voice phishing malicious app distribution sites have a fairly short life cycle. Thus, it is very difficult to secure a live distribution site. After a month of persistent pursuit, financial security firms have been able to collect malicious apps impersonating various financial companies in real time. As a result, we have collected about 3,000 malicious apps. In addition, we're collecting around dozens of additional malicious apps a day. After thousands of malicious apps were acquired, malicious app classification was essentially needed to identify the same malicious apps and similarities between malicious apps. Malicious apps can be classified by two typical characteristics. The first is the command and control information, aka CNC information. CNC information is hard-coded inside the app. The second characteristic is the phone intercept code, which is the app's main function. There are two reasons why we use these two characteristics as the classification criteria. First, the variations between malicious apps are not significant because they are core functions. Second, the algorithms are different by the developer, although the functionality is the same. Thus, we decided that they are the most suitable features for classifying malicious apps. As shown in the slide, KeySec classifies the CNC hard-coding types into 9 types and the telephone intercept code types into 10 types based on the class name. This slide shows an example of malicious app which is packaged by QIHU. When you upload it to JEB Dynamic Debugging tool, you can see that the app is not analyzed because the DEX code is hidden. If the DEX code is hidden, this app should be processed through unpackers. Packed apps from Chinese company QIHU 360 have different parts than regular apps. If you look at the manifest, where you can see the app's permissions and components information, you can see the Android Chihu section, which is not visible on a typical Android app. This additional part makes it difficult in decompiling. Assets folder contains integrity and dynamic packing related files like Apk and ripgi gu.so. The static analysis cannot read package name part in the packed DEX code. Thus, codes associated with the actual malicious behavior cannot be seen through static analysis. Let me explain the unpacking process of packaged apps. There are prerequisite tasks to be done before performing tasks in the slide. First of all, QIHU 360, which is an app related to Unpack, can be downloaded on GitHub. After installing the NDK of Android using the Unpacker uploaded on GitHub, and installing the native Unpacker, we performed works on the slide with the cases file installed in the folder. After completing this prerequisite works, attach ADB to a rooted Android phone or a rooted emulator and launch a malicious app. After that, check whether the process is properly uploaded. Then, unpack the case file extracted from the Unpacker released using the package name within the malicious app. After the unpackage task finished, then package name.dump.dex file is produced. The setting for dynamic analysis is finished if you upload the dex file on JEB Dynamic Debugging Platform. ADB is a multi-purpose command line tool that allows you to communicate with your device through the Android debug bridge. ADB is used for various tasks such as installing and debugging apps. In addition, ADB provides access to the Unix shell, which can be used to execute various commands on the device. You can download ADB from the Android SDK Platform Tools page. This slide shows the screen of uploaded the unpacked dump file to the JEB. As you can see, the DEX codes are shown unlike the previous slide. Manifest is a list that provides the system with essential information about the apps that the Android system needs to obtain before executing the code for the app. Manifest files can contain a lot of information, such as components, permissions, and the hardware and software required by the app. Among them, the app's package name, activity, service, broadcast receiver, and content provider must be declared. Usually, before analyzing a malicious app, we identify the Android name and execution authority in the action through manifest file. Check the location of the main app. Then we start analysis. In the picture of this slide, you can check the privileges, actions, and services of the app within the manifest file of the com.kpo.help package. The app disguises as a spyware scan application from Korean National Police Agency. Thus, the app includes Korean Police UI as its icon and includes KPO in the app name. This code intercepts IMEI information and MAC address through getIMEI and getMAC functions. If you look at the getIMEI function, you can see that getDeviceID function in ARG3 brings the International Mobile Equipment Identity Number and save it in V0. The getMAC function takes the connection information of the system services, then returns the MAC address in V1 variable. The following code uses the getSMS function to steal SMS and contact information from infected devices. The getVoiceID function monitors whether the victim calls a specific phone number. You can even check the overseas location that's receiving the information. Now, I'll finish the presentation of Beijing uses for malicious app analysis. Thank you for your attention.